Okay, sorry about that, guys. Yeah, technical difficulties. Okay, yeah, I'm glad to see that so many people turned up to learn about 3D rendering stuff. This is great. It shows a lot of promise for the future. You guys might not be concerned about 3D rendering in your applications right now, but as we move into this future of like VR and AR, and even just having just more interactive formats, we're going to get a lot more 3D content. So that kind of brings us to my talk today, which is about the JPEG of 3D, bringing 3D scenes into your 2D Android app with glTF, which is a format created by the Kronos group, the same people that brought you OpenGL, OpenGLES, Vulkan, among other things. Who am I? I'm the face of VR. You guys might have seen this picture. That is me. No big deal. So my talk is split into 3 parts. So I'm going to introduce the 3D post feature that we added to Facebook this year. And then I'm going to give you kind of a deep overview of the glTF format, why we chose to use it over other formats, why we're excited about it, and why we think it's going to be ubiquitous, kind of like JPEG is on the web right now for 3D. And then finally, I'm going to go through a sample glTF renderer that I wrote up. I have like a basic kind of hello world application, and I wanted to share this code with you today, but unfortunately it's blocked up by Facebook legal review. So what I'll do is that when the legal review is done and I have the link to the GitHub, I will tell the Android makers, Twitter people to post it, and then you guys can see that code. But you can see the code in the slides while you're waiting. So this is basically what the feature looks like in Newsfeed. It's supported on desktop and mobile. And basically you have your 3D object that you can manipulate. We have this basic carousel camera right now, and you can zoom and interact with the element. So you can imagine there's a lot of different use cases why this is interesting, especially for brands. You could be Nike and have your shoe model there, or a car company that wants to have a tour of their actual 3D interior. And even for something as fun and playful as Lego. So there's tons of use cases for brands, and there's tons of use cases just for fun sharing elements. But the original use case that we wanted to support for this when we launched was the use case of artists that create stuff in VR. We have this program called Oculus Medium for the Rift. And it's basically a VR sculpting application. So we have a lot of amazing artists that create these great VR sculptures, and they want to be able to share their content on Facebook. So this is kind of one of the main motivators why we wanted to build in this support. So now they have this flow in Oculus Medium where you can just share your 3D creation directly to Newsfeed, and then be able to see it on your phone and have extend the reach of what the artist can do. So we didn't just make this only for our own internal apps. So we recently launched public support for glTF 3D objects. So basically what we support is what's called a binary glTF file, which is a .glb extension. And what it is just one file with all like the data packed into one single file. And you can drag and drop that onto the composer, as you saw in this video. And then it's basically exactly like an image or a video. It's a first-class citizen on Facebook, and you can set the background color and interact with it. So sharing 3D on Facebook is super, super easy right now, and us using glTF is a big deal for that format. So I'm going to go into the actual glTF format itself, and why we think it's the JPEG of 3D. So if you guys don't know, I guess he's kind of like my boss's boss's boss or something like that. This is John Carmack. He's one of the founders of id Software, and he has a huge, huge impact that he's had on the gaming industry, being one of the first pioneers of the first-person shooter. He's the CTO of Oculus, and he made some bold statements that, we need some kind of transmission format for 3D objects as we go into this kind of VR, AR future. And the Kronos group kind of stepped up to the plate on this one. So if you look at kind of the history of media formats, we'll see that major applications have driven the adoption of certain formats. So for audio, we had MP3 popularized by the Napster application, and we had H.264 video popularized by YouTube, and of course Facebook played its part with getting JPEG to be pretty ubiquitous on the web. And now for glTF, we believe that this is kind of the format for 3D on the web because of the properties I'm going to talk about later on in the talk. So we think that Facebook's adoption of glTF is going to be a big deal here, and it's going to really push the 3D authoring software to use this format and other engines and things like that to get on board with this. So why another 3D format? So, the issue with, there's tons of 3D formats on the market right now, and some of them are super popular, like FBX is super popular. This is something that, if you're a 3D author working in Maya or something like that, this is probably the format you work in. But there's an issue with that format being that it's not standardized, it's owned by Adobe. It doesn't support some of like the latest kind of, hip ways of, doing rendering, like, physically based rendering. And there's ambiguity because of the fact that they don't have a standard, so the implementations are inconsistent. So you might have one implementation, interpret your file one way, and then another one interpret it another way. And then of course it's not extensible because, well, it's extensible by Adobe, but it's not extensible by you, and you have to use their SDK, and then there's licensing, issues that you have to worry about there. OBJ, I believe it came out of maybe the mapping world or something like that. It wasn't originally made for the core gaming use case or 3D animation. But it's a very simple format, but it's not standard, and it doesn't describe scenes. I think that's the biggest issue there. It only describes 3D objects. So you can't have animations, you can't have complex lighting, things like that. So it's not going to be sufficient for what we need as a 3D format. So Kronos actually contributed another format that was supposed to be a standardized 3D format. It's called Collada, or .dae extension. And the problem with this format is it was designed as an interchange format. So it's a format that's supposed to be used in 3D artist pipelines, and not necessarily to be transmitted over the web. So it's not designed to be efficient. They used XML, so it's not as, it's a little bit more clunky to deal with versus the JSON format that glTF uses. And it just really wasn't, the way the data is structured, it's not structured in such a way that you can easily just pull in the data into the GPU memory. So what are the advantages of the glTF format? So it's designed to be compact to transmit. So basically there's just one big buffer. I guess you can have multiple buffers, but the idea is we just want to have a tightly packed buffer with all our mesh data, all our scene data, and you want to be able to just index into that buffer and say, look at this section, this byte offset, and then read this much data to find this thing that you need, whether it's vertices or index attributes or something like that. It describes full scenes, it's fast to load. The fast to load being because you're quickly parsing JSON, and you are just loading, one byte buffer into memory, and you don't actually have to do a bunch of copies or, maintain memory while you're loading. It's runtime neutral. So this was a big change in glTF 2.0. So right now there's two versions. Well, the original version was 1.0, and it was more geared towards, the WebGL and OpenGLES use case, and less so to the PC use case. Because it actually supported using OpenGLES shaders, so the GLSL shading language. And that's obviously not something that can be used easily in DirectX environments for PC. So what they did for 2.0 is that they went towards kind of, the new kind of future, not future, but like the current, bar for what we do for, shading and lighting, which is physically based rendering, which uses a more realistic shading model where we take physical properties like the roughness of something or like how metallic it is to determine how we light the actual scene. And actually, Lomegi, he gave a talk about physically based rendering. You can find it on YouTube. I believe it was at like the Autodesk event or something in San Francisco. So if you're interested in that, just like search for Lomegi physically based rendering, and he gives a big overview of physically based rendering. It's extensible, so you could just add a vendor extension in the JSON itself, and that will make it do a lot of awesome things. So the main benefit that we have there is that it allows us to specify new upgrades to the format. So for example, mesh compression was an extension that Google proposed through their Draco mesh compression extension, and now that's becoming a ratified extension by the Kronos group. So it started as a vendor extension, and then now it's actually a serious extension because we want to adopt it going forward. So a brief history of the glTF format. Basically, in 2015, October 2015, the 1.0 spec came out. It had a little bit of rough edges. It wasn't really platform neutral. And that feedback was given by the community, and then actually Microsoft was the one that proposed the physically based rendering extension, which eventually made it into core glTF 2.0. So Microsoft getting behind glTF was a big deal. Google getting behind glTF was a big deal, and then now of course us, Facebook getting behind it is also a big deal. So you can see that Microsoft, their Paint 3D application for Windows PCs supports glTF as their transmission format. And now we have it on Facebook, and of course, Google Draco extension came out, which is all great. So now we're actually in a pretty good position versus where we were like a year ago. There is actually a pretty robust glTF ecosystem. So we have like the creation tools, and some of these things are conversion tools. So like we actually open sourced an FBX to glTF converter. So that's a big deal because a lot of existing artists are working with FBX formats in Maya or something, and they want to be able to bring their content into glTF, into environments that consume glTF. So we allow that. But of course what we really want is we want all the authoring tools to export to glTF so that we can just use that format. And then you can see that there's been plugins and extensions created for Unity and Unreal, which are the two big gaming engines that everyone uses on mobile and otherwise. So having support for glTF at that level is a really big deal because then you can just pull in your 3D scenes from glTF directly into your Unity environment, and that's going to really turbocharge the use of the format. And we support it in React VR. It's built into 3JS, which is the popular WebGL framework for web. So it's actually really getting a lot of traction right now. So now I want to dive into the internals of the glTF structure and show you guys what it looks like. I'm going to show you a Hello World example that draws just a triangle, which is like the primitive for drawing with the GPU. It's just 3 vertices that you draw, and I'm going to show you what that looks like in a glTF JSON. So what is actually in the glTF file? So you're going to have basically your scene graph, which is basically a node hierarchy for what you're going to render, what the transforms are on each node, and it's also going to have materials and textures. So that's basically the stuff that you use to map on the meshes that you contain in the format. And it also has animation data and skin data. Skins being, if you have a character, you have a skeletal system that you use to transform when you're doing animations, like I have joints. So that data is going to be packed into the format as well. And then what happens is the renderer will take all this data and then consume it, and then it uses that to actually render the final scene using a GPU API, such as OpenGLES or DirectX or Vulkan or something like that. So the core glTF file, it's comprised of the .glTF, which is just a JSON structure, which has a strict spec that you have to adhere to, and then there's a binary file. So the binary file basically tells you, basically contains all your metadata and your indices. And if you don't know about how index drawing works in OpenGL, index drawing is essentially, let's say you were drawing a square and you need to draw it with 2 triangles. So you have basically 3 vertices for each triangle, so you'd have to draw 6 vertices, but you're actually sharing 2 vertices for that triangle, or for the square. So if you use index drawing, you can just specify the index of the vertex and then share those 2 vertices. So for a square, it's not a big deal, but when you have a huge complex mesh, you actually want to really share as much vertices as possible, so you use the index drawing. So you have a buffer that basically says, look at index 0 to find the vertex 0, and then look at vertex 1, and then vertex 2. And then that's how it specifies the triangles. So that's index drawing. And then of course there's textures. So for physically based rendering, the metallic properties, the roughness properties are all specified by shader or by textures. And I'll show you guys what that looks like later on. So this is the high level elements of the JSON, the glTF JSON structure. So you have your top level scene, and each of these things is going to be a JSON array of multiple scenes within the file and the root. And then you have multiple nodes that can be part of each scene. And then each scene can have multiple meshes, and then the meshes have an accessor. So the accessor tells you how to get data from the binary buffer. And there's reasons for why we have this much indirection. Basically, you want to be able to have multiple meshes access the same buffer. That's a key for efficiency. Because if you had separate buffers for each one, there'd be redundant information. You can't tightly pack the data. So a common thing, that we usually do in graphics is you might have like your vertices forward, like as a float, and then at the end of the vertex you also have like the vertex normals, or you might have the texture coordinates or something like that also stored in a tightly packed format. So you're able to specify like the stride that you're jumping through the buffer, by using this kind of abstraction. So it is a little bit tedious to like have to jump through all these indirection points, but it's really designed for efficiency. So this could be an example structure here where you have basically your root, you have a car, and it's like the top level, and then it has like wheels as its child. And the reason you want to do that is because if I apply a transform to make the car move, I want to apply that transform to the car level, and then I want the wheels to also move as well. But you can also have independent transforms on the wheels so that the wheels rotate, for example. So that's why you have this scene graph. And the scene also can contain a camera, so it tells you where you're looking, in the scene, because you can have different perspectives. So all that is specified within glTF. So now I'm going to get into our hello world.glTF file and show you guys what this actually looks like, and it'll probably be a lot clearer to you. So what we're going to do is we're going to specify a scene that just draws this 2D triangle using glTF. So this is what it looks like from the JSON. So you have your scenes, and note that you have all these JSON arrays for the top level stuff, such as the scenes, the nodes, the meshes. But within those, we actually reference other objects. So for example, in the scene sections, it has a sub-dictionary that has the nodes. And the number there is actually indexed into the list of nodes. So in your list of nodes, you're going to have all the possible nodes, and the scenes might reference any one of those nodes within that list. So again, this is, it is a lot of indirection where you have to follow kind of the index pointers, but it's actually designed to be parsed really quickly because of the fact that you can just inflate these lists and then just index into the list to get the values that you want. So this is a big improvement over something like an XML structure, which can be very hard to parse and tedious to go through. And so under the mesh section, there's a little bit of intricacy there. So we have our primitives. So a mesh can be comprised of different primitives, and each primitive can be essentially a draw command in graphics or in OpenGLES, for example. So why you want to do that is sometimes you can have a mesh that is so big and complex that it actually won't fit into a single OpenGL draw call because it maxes out the index buffer or something like that. Because we use generally we use short indices. So you have it's kind of like the issue that we had on Android a while back where you have 2 to the 16 to work within. So if you max out 2 to the 16, then you need to segment your stuff into multiple primitives. And there's other reasons why you might want to do that as well. So the attributes, if you're not familiar with OpenGL shaders or shaders or shading in general, attributes are just inputs to what's called the vertex shader. So the vertex shader is basically the thing that tells you where to put a vertex in space. So it's a program that runs on the GPU for every single vertex in your mesh. So what this attribute section is trying to do is it's trying to tell you which accessor do you need to go to in the JSON to find the byte buffer address that you need to look up this data. So the position here is talking about the vertex position. So this is essentially telling us where do we find the vertex data in the binary. And then similarly, the indices section is telling you which accessor index that you need to look up to find all the indices that you need to tell you how to actually draw the contents of your vertex buffer. So the buffer section here, it's a little bit interesting. So you can actually, in real generic glTF, you can specify the URI, so you can actually have a web URL for your binary buffer, or you can have a local file. But for our Hello World use case, we just use a data URI. So all the data, because it's only 3 vertices and 3 indices, it's super easy to just pack that into a data URI, and that's all we're going to handle parsing in my sample code later. And then we specify the byte length, so it knows how much we have to read. And then the buffer views, like I said, the buffer views it's telling you an abstraction on top of the buffer. So I have this one fixed length buffer, and I might have a buffer view that looks at the front half of it, and then another one that looks at the second half of it. So the front half might have the vertices, and then the second half might have the indices. So that's how that works. And of course, it gives you the byte offset and the byte length, so you know how much to actually look at. The target here, it's just telling you, these are actually OpenGL values for whether it's an array buffer or an element buffer being the index buffer. And if you guys aren't familiar with OpenGL, probably looking at the sample code in its entirety will help you to understand exactly how this stuff actually works, because I know it's kind of cumbersome to approach something like OpenGL rendering. Now the accessors essentially tell you which buffer view to look at, and it tells you what the content type is going to be. So for example, for indices it's just scalar, so you're just looking at individual like short int values. And for the vertices, we know it's going to be a vector of 3 elements. And within the actual buffer view that we saw here, the component type tells you if it's like a float or if it's an int. So those things just map to the actual value, so you know how many bytes that you have to look at. And then the min and max are basically just the bounding box of like your sample set. And of course, the asset version is important. That's the glTF version. It tells the parser and renderer what kind of glTF you're rendering. So that's the hello world JSON. I was going to talk about PBR. So PBR is basically a way to do realistic rendering of your objects in your scene using physically based properties. So for example, the roughness of something can tell me how much light should reflect from it and how, the kind of feel that it has. So there's a bunch of, mathematical formulas that we use in the actual shaders to provide this. But essentially what the author has to do is extract the texture data into the base lighting model, so like without any shading, and then give us the metallic and roughness data as textures. So you might not know how to do that, but I actually don't even know how to do that myself, but that's what like the 3D designers do. So this is kind of the new way we do shading these days, which is a more realistic and gets you that kind of real look, and then you can draw the lighting from the environment and have it do reflections and things like that. The other important thing about glTF is the Draco compression. So I talked about it being the JPEG of 3D. So one of the key elements of that is we need encoding and decoding just like JPEG has, so we can have the smallest possible transmission over the web. So Google has done some amazing work here with the Draco compression extension. So these are sample models from the Chronos glTF GitHub. So it's a bunch of sample 3D scenes. And Google is able to get 10-to-1 compression ratios for some of these meshes, just like packing it down, which is actually pretty good. So you can have the 30 megabyte mesh you compress down to 3 megabytes over the wire, and then you just do a slow decode or a little bit of a decode step before you actually load it on the client. This is great because your bottleneck is always going to be the network transfer when you're doing you're pulling these glTF files over the web. Okay, so now I'm going to actually go into some sample code so I can kind of relate, the actual JSON to, actually physically parsing the data and then rendering it using OpenGLES. And again, like if some of this stuff goes over your head because you're not used to OpenGLES rendering, the sample code will be available in the upcoming weeks or so. This is a really bad video that I shot in my hotel of me demoing this renderer. So basically, I just took like the AR core sample that renders an object onto a surface. So it's using like SLAM to locate surfaces. It shows you a plane, and then you click on there, and then you can place something on that surface. So that's what I've done. So I basically wrote this little glTF parser that can parser and renderer that can render this hello world.glTF file, and it renders my triangle, which is great. And again, like because there was no material specified in the glTF JSON for the hello world example, we just used the default shader. So normally the default shader is going to be like gray or something. So the color of the triangle should be gray, but I just used red because why not? So this is just me adding these glTF scenes, which is just a triangle, very simple. My renderer is definitely not a complete spec complying renderer. It's actually pretty complex to write one, but I believe Java GL, the project, has a glTF renderer. But this is more for educational purposes that I'm putting out this code. So the first thing we have to do is parse the glTF. So we saw the structure. It's pretty straightforward. What we need to do, we need to extract that data and then use it to actually look up the actual buffers that we need to pass into OpenGLES when we're doing the rendering. So remember, this was our structure. So we're going to parse a bunch of JSON arrays to get this data, and then we're going to follow the indices of the different elements to go get values. So if you guys can't read this, basically all I'm doing here is I'm reading in the JSON file using the JSON object. I don't know what package that comes from, but it's built into Android now. I know that other people use different JSON libraries. And all it's doing is it's just grabbing the JSON array for these top-level JSON objects. So the scenes, the nodes, the meshes, the buffers, buffer views, the accessors, and then it stores it in an array list within a top-level glTF scene object. So just Pojo parsing right here. And there's ways to do this automatically too. I believe that's actually what the Java GL implementation does. And probably there's some cool way to do this with Kotlin, but I don't know Kotlin, so I don't want to do that. All right, so what we're going to do is for each one of these sections, and I'm just going to talk about parsing nodes, meshes, and buffers, because those are the most interesting ones. You guys can look at the code later. So parsing nodes is pretty straightforward. Again, all you need to do is find the indices of the meshes that are part of the node. So that's pretty straightforward. You just look at each object in the list of nodes, and you get the int value for the mesh, which is basically just a reference or an index into the list of meshes. So, of course, when I go and parse my meshes now, I need to also get all the list of primitives, because like I said, a mesh can have multiple primitives that make up the actual data that we're going to be drawing. And each primitive, again, corresponds to one draw command in OpenGLES. So once we get the primitives, we're going to get their attributes. And again, attributes are the inputs to the shader that you're going to pass into OpenGLES or whatever rendering library you're using. And in our case, we're going to get the position attribute, which is basically the vertex position for each vertex in your mesh. In our case, it's just a triangle, so 3 vertices. And then your index buffer, so each one of these is going to reference an accessor. So when I get this primitive.indices, this is getting an int value, and that int value is just an index into the accessor. So I told you there's a lot of indirection for performance reasons, but in the end, it's pretty straightforward. We're just parsing out these values and looking up the stuff that we need to render. So in parsing the buffers, this is a little bit interesting too, because in our case, we're just handling the data URI use case. So what we're going to do is we're just going to parse out the data URI and then store it in a buffer. What we're not going to do is we're not going to make copies for each buffer view. So instead of making a byte buffer, a separate byte buffer for the index buffer and then another one for the vertices, we're just going to use the same byte buffer and really look at it as a view into the buffer. So it's an abstraction on top of the buffer. So you only have one buffer, you allocate one buffer, and then all you need to do is look at the offset into that buffer. So you're saving a lot of memory here during the load time. And again, all we're doing with this data is now we need to upload it to the GPU, because that's what the GPU needs to actually render the 3D scene. So the next thing we're going to do is actually create the render objects now that we've parsed the actual glTF data. So how that's going to look like is we're going to go over each of the mesh primitives, and then for each mesh primitive, we're going to follow the indirection of the accessor to the buffer view and then to the buffer, and then we're going to provide the reference to the actual buffer that we need when we specify it when we do the OpenGL upload of that data. I know that sounds complicated, but it's not that bad. So again, one render object per glTF mesh primitive, because each render object is going to correspond to one GL draw command. And then your index buffer and your vertex buffer is going to be data extracted from the accessor. So let's look at how that works out. So again, we have a top-level scene, and we're just going to traverse the meshes in that scene that we parsed out already. And then we're going to get each mesh, and then we're going to get each primitive for that mesh. And then the interesting part here is where we look up the position index accessor. So that's an index to the accessor that we're going to look up in the top-level structure again. So that allows us to look up the buffer view, and then now we can look at the buffer. So this is basically the core of how you follow the indirection to actually get down to the raw bytes that you need to get the vertex buffer and the index buffer. So that's what we're doing here. So in this part, we're actually uploading the data to the GPU. Oh no, sorry, we're just storing the data. So all we do here is we take that exact same single buffer, and we know that for the vertices, because it's in the component type, that it's going to be a float buffer. So we can interpret it, the buffer as a float buffer, but it's still just looking at the same array of bytes. And then we specify the buffer view's byte length, so it knows for the vertex buffer, for example, we're just looking at the first 6 bytes or so. And then we have the byte offset, which will be 0 for either the index buffer or the vertex buffer, and then it's going to be, 6 or 8 for the index buffer. So we're just moving down the buffer and finding the things that we need. So once you have that, then we just reset the position pointer to the beginning of the byte offset. If you guys haven't done work with byte buffers, this is kind of the tedious stuff that you have to do, because once you move the pointer down, you need to reset it to the beginning, otherwise you're going to be reading the wrong data in the buffer. So now once we've done that, then we can actually do the upload of the data. So if you've done any work with OpenGLES, you know that we need to provide the actual CPU memory buffers to the GPU so that the GPU can work with it at render time. So what we do here is we bind our buffers. So we create buffers with glgen buffers command. This allocates memory on the GPU, and then we upload the data using the gl buffer data command. So what that is doing is it's telling it that we're going to look up this buffer at this byte offset, and we're going to provide the buffer to the GPU. So it's basically just going to read the data at that byte offset and then upload it into GPU memory. So the great thing here is that we didn't have to do a separate allocation for every time we do this upload. We only have the allocation on the GPU side. Everything else was just done with one buffer. So now how do we actually draw this? So if you've never done GL drawing, we have to attach the shaders. So this is the default shader that we have for this scene, because we didn't actually look up any materials. So in our case, we're just going to use the red color for our fragment shader, which is the shader that provides the color for every pixels on the screen. And we're going to bind the buffers that we just created. So we just created a vertex buffer and an index buffer, and we're going to bind those so that when we use the glDraw elements command, that it knows what to render. And that's pretty much the gist of how we render this 3D scene. So what we're going to do here is we go over all the render objects. So remember, we just created a list of render objects, and we're going to bind the element buffer, which is the index buffer, and then bind the vertex pointer, which is going to bind the vertex buffer. And then we execute that glDraw elements command, saying that we're drawing triangles, and we give it how many indices that we're looking at, which is going to be 3 for each of the 3 vertices that we need for the triangle in this case. And this command essentially does the work. So that's pretty much it. That's the glTF sample renderer. Now, of course, it's a lot more complicated when you do like a real complex, animated, I don't know, inside out character or something like that, and you need, crazy lighting and all kinds of, intricate animations for like the face, morphing and things like that. But in the core, this is essentially how the rendering works. You have buffers of data, you access it, you upload it to the GPU, and then you render it. So that's all that the glTF format is abstracting. So in the end, that's what we get. We've rendered our triangle using the data that's in the glTF file, and that's exactly essentially how this whole thing works. And yeah, that's pretty much my talk. I know like this stuff is kind of, if you haven't done OpenGL rendering, this stuff can kind of go over your head, but a lot of this work is like you write it once and then you basically just call, glTF renderer.draw, and that's essentially what most of these APIs are going to be. So if you use like Java GL, it's going to have an object, it's going to have a render object renderer, and basically you just need to provide the data, whether it's a glTF file or an OBJ file or some kind of other file, and then you just need to render it in a valid rendering context. So you might be using a texture view or a surface view or something like that that has a valid OpenGLES context, and then you can render that. So in this case, we're just rendering in the context used for the camera, which is pretty straightforward. So yeah, that's pretty much it. So anyone have any questions about this? Over there?
I was wondering if the JSON file is ordered, because maybe I just made a parallel which was not accurate, but one of the great things of JPEG is that the progressive loading. So it's loads the stuff in the beginning. So here, for me, JSON is not ordered, but maybe they changed it to be ordered. So because you are loading a graph, is it ordered or not?
So that kind of touches on a few different things. There is future work that is going to be looking at like streaming. So I think that kind of gets to the heart of what you're trying to ask, which is, how do you, if I have this really, really big complex scene, I don't necessarily want to try and load this entire, actually for, if you guys know about Oculus Quill, it's like a VR drawing application that we have. And some of the art that comes out of there is like 500 megabytes of 3D mesh data. So you wouldn't want to load all that at once. So one of the things that we want to have for glTF is a streamability, the same way you can stream video. So that hasn't been done yet. We do need to read the entire JSON file for it to be valid right now. But we can see, probably in the future you may be able to break stuff down where I could look at different scenes and then just load the stuff I need for scenes. But one thing you can already do is, remember I said the data binary pointer, it can just be a URI, right? So you can just say, I need to go look up this data, and you can have multiple different web links to the actual binaries. So, and this is how it works for textures, right? For textures, you can be fetching them over the web. So you're effectively are progressively loading. And then your texture data is probably going to be most of your data anyhow, because it's the biggest element. So you're already kind of progressively loading it.
Yeah, I was just wondering, because you mentioned that JSON was used over XML for glTF, but I was wondering, do you have any idea why it was not something like protocol buffers? Because as far as I know, those are much more performant.
Yeah. Well, I mean, the key here is that in the JSON itself, we're not really storing all the data, right? The data is a separately tightly packed thing, which is equivalent of something like proto buffers, right? Because everything is tightly packed vertex and index buffer and all the data that you need, so it's already packed as tight as possible. And then when you use mesh compression like Google Draco, that's even compressing it even more. So the actual JSON part, all that it has is the scene graph. So it's just telling you the structure of the JSON. It's not actually the data. So you would use proto buffers for encoding data, but we already have a tightly packed format for data.
All right, thanks.
Oh, and then one of the reasons why we want that kind of format for data is we want to quickly be able to just use the OpenGLES upload command with that buffer. So the OpenGLES GL's buffer data command, it just takes a float buffer. So if you have a float buffer and I give it a byte offset, then it'll just copy the bytes that you told it to copy from that byte offset. So now I can just have one buffer index into that directly. All I did was just create that one buffer. And other formats like XML have the issue where you create multiple buffers for everything that you're loading. But in this format, we just load the binary data exactly as it's loaded in the GPU. So you wouldn't want to have to translate from the proto buffer format to that format. Anyone else? Cool, thank you. Actually, I have one plug. I noticed that there's an AR